Hey everybody, welcome back. Hopefully you had a chance to get some additional homework questions answered if you had some curve sketching homework questions. Um, if we finish a little early today, you may have an opportunity to ask one or two more. We'll have to see. We're going to be today going over one more application of derivatives. Next week we're going to be going over, we're going to be finishing this one up and doing two others. And then we're actually going to be leaving derivatives behind, sort of. We're going to look at the other half of calculus. So the first half of calculus is derivatives. The second half of calculus is something else. So we're going to get to that following next week. So next week we're going to go through the rest of the applications. There are lots of applications of derivatives, so this is not exhaustive at all. But the application we're going to do today is actually one of the most practical applications. Now, some of the examples that we're going to look at, you may look at that and go, is that really practical? I don't know if I can answer that question, but there's a lot of uses of this type of application of derivatives. And so the title of this is section 3.7. So it's optimization. Let's see if I spell that right. Optimization. The idea behind this, let's go back way to the beginning of chapter 3. Part of the idea behind, one of the sort of practical ideas behind doing finding derivatives is if I have some sort of function that's sort of kind of like a real world function, like stock market or profit or cost, I'm typically looking for the highest and lowest points for some reason. If it's profit, I want to maximize profit. If it's cost, I want to minimize cost. If it's stock price and I'm wanting to sell, I want to find the maximum price where I'm at so I can sell, that kind of thing. So there's a lot of situations where we want to find the biggest, the smallest, the best, those types of things. And we call those types of problems optimization problems because we're trying to find the optimal solution to something. So I've prepared these problems. Admittedly are word problems, so we're walking back into word problems again. I think these are the only word problems left in this chapter. I've prepared a checklist for you for how to approach these problems, kind of like we did with curve sketching, kind of like we did with related rates. I will warn you that you don't get to have this on an exam, but this will help you kind of get in the groove of doing optimization problems. And once you do that, then I think you'll get it under your belt. You won't need the checklist anymore. But we'll go ahead and pass this checklist out just so you have that. And we're going to see how to approach these types of problems while going through this checklist. Okay? So I'm going to start with an example. Some of the examples are actually going to come out of the book. So if you don't have your book open, go ahead and open your book. Let me give you a minute to do that. Go ahead and fish your book out. Open to section 3.7, and specifically we're going to be on page 216. So take a look at page 216 in your book. So I'm going to do my first example of an optimization problem. I'm going to do kind of a modified version of number 2 here. All right. So the problem, actually, this one's not that long, so I'm actually going to write it out. I want to find 2 positive numbers. Okay. Such that the sum is 40. This is where I'm modifying the problem. I want to find 2 positive numbers such the sum is 40 and the product is as large as possible. Okay? So I want the sum to be 40 and the product to be as large as possible. Okay, now the key word here, you'll see this in your handout. The types of words you're looking for are best, highest, lowest, most, least, largest, smallest. So the fact that I'm asking you for something that's as large as possible, that's my indication that I have an optimization problem here. Now, just so I don't want you to do this in general on these types of problems, but before we had calculus involved here, what you would typically do probably is just guess if I give you something like this. So you might say, for instance, if I need the sum to be 40, let's take the numbers, for instance, 1 and 39, and their product, which means multiplying to get them together, gives me 39. Okay? Well, that's not too bad. Let's pick another pair. If I took two numbers where the sum is 40, like 10 and 30, well, 10 times 30 is 300. Well, that's a whole lot better than this thing. So that's better. What if I did 15 and 25? 15 plus 25 is 40. 15 times 25, well, now I'm going to have to, how do I do that in my head? 75, 375? Well, that's better. What if I did 20 and 20? Well, 20 times 20 gives me 400. So you can see I'm just kind of guessing. I don't really know what two numbers are going to give me that best product. So there's got to be a way to do this so that it truly is, it's not just kind of guess and check. Okay, so let's go down our list and see what's going on here. So read through the problem. We've done that. Maddie, if you want to, or Zach, if you want to add cry at the beginning, that's like part 0. That's fine. So we read through the problem. We cried. Draw a picture if possible. In most of the ones that we're going to do, that will be possible. Here, we don't really have. That's not really possible. Now what we're going to do is identify the quantity that we want to maximize or minimize. So I actually want you to write down, when we do these problems, I want you to write down a statement like, we want to maximize or minimize. In this case, we want to maximize. We want as large as possible. We want to maximize the product. Let's just give that a name. That's the product P. Okay. So that's clear from the problem. We want to take the product and get that as large as possible. So then we come up with a formula for P. So if we call those two numbers x and y, P is x times y. And the idea now is I want to find the maximum of this function, but we have a function with two variables in it. We don't know how to do stuff with two variables. You won't until you take multivariable calculus, if you do. So what we need to do is we kind of need to intermittently get this function just with one variable, and then we can do our calculus to figure out where the maximum is. Okay, so we have to use extra information that's given in the problem. And so we know from the problem, we know that the sum, x plus y, is 40. So what I'm going to do is I'm going to use that information to eliminate one of these variables. I'm going to use this information. I'm going to solve for one of the variables. So if I put the x on the other side, y is 40 minus x. And then I'm going to take that and put that in for y. So the product is x times 40 minus x. Okay? So what that now does is this gives me, let's maybe multiply that out, 40x minus x squared. Now I have the product as a function of x. And when you give me a function of another variable, I can find the max or the min using calculus, using the techniques that we've had up to this point. The way that we do that is now we're going to maximize or minimize the formula. So we're going to take the derivative. Okay, typically for finding maxes and mins, we're going to take the derivative. Now, I'm not going to write p prime. The reason is that I've got lots of variables flying around here. So I'm going to use the Leibniz notation that we're used to seeing, dp dx. If I'd solved for x and put that in here and I only had y's, then I would write dp dy. Okay, but it's much better to use this notation than just prime because I don't know what I'm taking the derivative with respect to. I've got the other variables flying around. So we're just going to write, we're going to use the Leibniz notation, dp dx, the derivative is, derivative of 40x is 40, and the derivative of x squared is just 2x. Okay. And so now I'm going to set that equal to 0 and solve. So 2x is 40, x is 20. And so now I'm going to check the derivative is 0 at 20. And here's the derivative. If I check points around there, for instance, if I were to plug in 0, that derivative is positive. If I plugged in a really big number, like 40, that number is negative. So I want you to notice it's increasing and then decreasing. So that means that 20 gives me a maximum product. And that's exactly what we were looking for. So x equals 20 is going to give me a maximum product. Now x plus y was supposed to be 40. So if x is 20, y is 20. So the two numbers that I want are 20 and 20, and that gives me a maximum product of 400. That's the maximum product that I can get. Does that make sense? So the idea is when we're given a problem where we want to optimize something, we basically need to get a formula for it in one variable and then use our calculus techniques to find the maximum or minimum, whatever the problem is asking me for. Okay? Does that make sense? Sounds easy. These things can get as complicated as you can imagine, especially because real life is never simple. All right. So what we're going to do now is I've got 3 other examples that we're going to run through. Let's take a look at number 7 on that same page. So page 216, number 7. All right. Number 7 says, find the length and width of a rectangle that has the given perimeter, that has a perimeter, in this case for number 7, 100 meters, and a maximum area. So I want a perimeter. So the perimeter is 100 meters, and I want a maximum area. And I have a rectangle. So we've read through the problem. If somebody wants to cry, that's fine. There's no crying in baseball, but sometimes there's crying in calculus. And that's okay. But we can all do it. All right, so taking a look at our checklist, we're going to draw a picture here. So in this case, we have a rectangle. And we're going to label it with what we're interested in. So we've got the width and the length. So we're going to go ahead and label there. Okay, and then the first thing we need to do is, because this is an optimization problem, we need to figure out what we're trying to optimize. So we want, and I know this might seem hokey, but I totally, every single time, want you to write down, we want to, in this case, maximize the area, and we're going to give that a name. Part of the reason that I'm having you write that down is that there are going to be some problems where you're trying to find a maximum, and you end up going through this work, and you get a critical number, and it ends up going like this, and you end up finding a minimum, and that's not good. So like, for instance, if you were supposed to maximize profit, if that was your job, and you use calculus techniques to do it, and you ended up finding the minimum profit, and you told the person that was the minimum, that would be really bad, and you'd probably get fired. So we have to make sure that we're checking, are we looking to maximize or minimize something? And then when we get to the end, double checking that that's actually what we did. Okay? Don't fluff over that. That's actually super important. So we're going to find a formula for what we're trying to maximize. We're trying to maximize the area. It's a rectangle. So obviously the formula is length times width. Now we have a function of two variables. I don't want two variables in there. I want one variable so I can use my calculus that I know. So I need to pull out extra information that we have. And the information that we have is that we know that the perimeter is 100, but the perimeter is 2 copies of W and 2 copies of L. So 2L plus 2W is going to give me 100. So I need to solve for one of those variables and put it back in here so I get a function of just one variable. It really doesn't matter in this case. They're both just as easy to solve for. So let's solve for L. So I'm going to put the 2W on the other side. So I'm going to get minus 2W there. Then we're going to divide through by 2. So 50 minus W is L. And I'm going to take that and put that in for my area there. So my area is actually 50 minus W times W. In other words, my area is 50W minus W squared. Okay. So now we have a function of one variable that I'm trying to find the maximum of. So now we're just going to use our calculus techniques to maximize or minimize. So we're just continuing down my sheet here. So the derivative, again, don't write A prime. Let's write the ADW because W is our variable here. It's going to be 50 minus 2W. If I set that equal to 0 and solve, 2W is 50, so W is 25. And again, we need to check and make sure that we truly are maximizing that area. We don't want to minimize the area if we're supposed to maximize it. So here's my derivative. If I were to plug in something smaller than 25, like 1, I'm definitely positive there. If I were to plug in something bigger than 25, like 50, then I've got 50 minus 100, that's negative. So did we do what we were supposed to do? Looks like it. So we're supposed to maximize the area. We get maximum when the width is 25. And when the width is 25, going back here, that means the length is 25 too. Okay, so that means our rectangle, and we should pay attention to units here. So our rectangle is going to be 25 meters by 25 meters. In other words, it's actually a square. And that's actually one thing that's interesting is that for a fixed perimeter, this is actually what number 8 shows. For any fixed perimeter, the best area that you can get is always a square. So if you have, for instance, we'll get to this later, but if you have a fixed amount of fencing and you want to make the maximum area you can, you should make a square if you're going to make some sort of rectangle. Don't make it long and thin or short and fat or something. You should make a square. That turns out to optimize the amount of area that you have access to. Interesting. Okay. Let's go ahead now. I'll go ahead and give you a 5-minute break. Let me erase this. And then we're going to do 2 more problems here. So you'll want to stop the video here if you haven't already. Okay, we're back. So the third problem that I want to do today, we're only going to do 4 total, So the third problem I want to do is number 20. So if you've got your book open, take a look at number 20. I'm not going to do all the various parts because they kind of have you try some things. Let's not do that. We're just going to kind of jump in and do the problem. So we want to make an open box from a square piece of material by cutting equal squares from the corners and turning up the sides. We actually had a problem like this way at the beginning of class when we first started back in the fall. The idea is we've got a piece of paper that's 24 inches on each side. So what I'm going to do is I'm going to first draw it here. It's square. Okay, 24 and 24. And then we're going to take it and we're going to cut out corners. And they've conveniently told you that those are squares as well. Each side is x. And then what we're going to do is we're going to fold. So let me now draw this kind of more flattened. So we have these squares cut out here. Okay. So once those are cut out, what that does is it makes this almost kind of like a little cross thing. So then we perforate right here. And then we fold those edges up. Right? So we get something like that. Now, obviously, if we make these squares bigger, that's going to make the sides taller, but it's going to make this middle area smaller because we're cutting away more. So the issue is, what it's telling you is, I'm going to skip to part C. Use calculus to find, well, I guess we want to find, you can kind of see it in part A, they should state this just clearly, but we want to maximize the volume of this box that we're creating here. Okay? So the first thing I'm going to write down is we want to maximize the volume of that box right there. All right, and the volume of a box is the length times the width times the height. So length times width times height. Now obviously the length, the width, and the height are all going to be related to x in some way, so we're going to fill this in. So let's start, and let's notice that when I cut these away and fold, the length of the subsequent box is actually right here. The width is right here, and they're actually the same because we're talking about a square and we're taking away squares. So the length and the width are actually going to be the same. Overall, this thing is 24, and we're pulling away x and pulling away x here. So this length right here is actually going to be 24 minus 2 copies of x. So that thing right there, this length, is going to be 24 minus 2 copies of x. Got that? Is that clear? This is 24. I'm pulling an x away, and then folding this up. So the width, this width right here, which is this width right here, ends up being 24 minus 2x. Same thing for the for this width right here. So 24 minus 2x. So each of those is 24 minus 2x, 24 minus 2x. Then the height is what I get when these sides fold up, but the side is just x, so when I fold it up, this height is just x. Okay, so I get 24 minus 2x, 24 minus 2x, and x. That's my volume. And that's what I want to maximize. And it just has one variable in it, so that's awesome. I kind of like not dealing with the product rule. So I think I'm actually going to multiply this out um, just to make my life just a little bit simpler. 24 times 24, well, 12 times 12 is 144, so 24 times 24 is going to be 4 times that. So I'm going to get 576. Okay, I'm just multiplying these two out right now. So foiling, I've got first, outer, inner. So outer is 48x, inner is minus 48x. So I get a total of minus 96x plus 2x times 2x is 4x squared. So if I throw that x in there, all right. So 576x minus 96x squared plus 4x cubed. Okay, so now I want to find I want to maximize this. I've got a function, so I'm just going to use my calculus. So when I differentiate, again, don't write v prime. The derivative here is just going to be 576 minus 96, and then that x squared is going to become a 2x plus 4, and then the x cubed is going to become 3x squared. So I've got 576 minus 192x plus 12x squared. Okay. Now, it turns out that all three of these things are divisible by 12. So to make my life easier, well, first to make my life easier, I'm going to switch the order of the terms because I don't like factoring when the constant term is first. Let's pull a 12 out of here. If I divide 96, well, 96 times, 96 is 12 times 8, so 192 is, we've got a 16x here, if I pull 12 out, plus, we got 576 by taking 24 times 24, so if I took 12 times 48, that would give me this number as well. So got x squared minus 16x plus 48. Okay, so I want to know where is this derivative equal to 0, so I'm setting this first part equal to 0. And if I factor that turns out to factor as x minus 4 times x minus 12. Okay. So x equals 4 and x equals 12. So that's where the derivative is 0. Now I want to point out something here, and this is something it's actually true in some of the previous problems too, but when we encountered this problem long time ago, one of the things that I pointed out was that there's only so big that x can get. Definitely x can't get any bigger than 24. If this side has side 24, I can't cut more than 24 away. But since I'm doing it on both sides, actually the biggest x can get is 12. Okay, so we're not going to actually have anything bigger than 12 here. The smallest x could be is 0. I could just not cut anything. So we're not actually going to check anything beyond 0 either. So really, these are the regions that we need to be checking. And if we check those regions, here is the derivative, okay, which is actually just 12 times this thing. If I were to plug in something small like 1 minus 16 plus 48, this is definitely a positive number, so I'm going to get positive here. And then if I plug in something bigger than 4 but smaller than 12, like 8, I get a positive number here and a negative number here, so we're actually going to get a negative derivative there. So in fact, we did find the maximum volume. The maximum volume is when x turns out to be 4. So x equals 4 gives me that maximum volume. So let's check and make sure that we're answering the question then. So use calculus to find the critical number and find the maximum value. So we want to cut away, so that our units are inches, so x is 4 inches, so we want to cut away 4 by 4 inch squares from the sides. Okay, 4 by 4, 4 by 4. Okay, and if we cut a 4 by 4, just so you can see this, the box that we end up with is, if x is 4, 24 minus 8 is 16 by 16 by 4. That turns out to be the best box that we can create this way. All right? Does that make sense? All right, so now I've got one more example to do, and we will be done for today. That example is actually number 24. Okay, so number 24 is our last one here. Okay, so let me read number 24. A rectangle is bounded by the x and y axes and the graph of y equals 6 minus x over 2. See figure. Okay, so they've got a figure here. You notice that that line goes through, on the y-axis, it goes through 1, 2, 3. And on the x-axis, it goes through them 1, 2, 3, 4, 5, 6. So we've got a line here. This is the line y equals 6 minus x over 2. I mean, it's negative 1/2 x plus 3 is another way to write that. It's got a y-intercept of 3 and a slope of negative 1/2. And so we've got a rectangle that's bounded by the y-axis and the x-axis in this line. In other words, if you pick a point on this, then we've got a rectangle here. Okay. Now you'll notice that if I pick that point up here, I would have a tall, thin rectangle. If I pick that point way over here, I'd have a really wide but narrow rectangle. So what it's asking me to do now is, it says what length and width should the rectangle have so that the area is a maximum. So in other words, we want to maximize the area of this rectangle, A. And the area, let's call this part x and this part y. So that area is going to be x times y. But we know that the relationship, we've got an area, a function with 2 variables. I want 1 variable, so I have to get rid of one of these variables. But we know the relationship between x and y equals, at this point right here, this is the point x, comma y. That point is on this line. So y is 6 minus x over 2. So I'm just going to sub that in. Y is 6 minus x divided by 2, so it's 1/2 times 6 minus x. Okay? So now I have an area with 1 variable. Let's clean this up just a little bit. I've got x times 1/2 times 6, so that's 3x. And I've got x times 1/2 times negative x, that's negative 1/2 x squared. Okay. So now I want to find the maximum for that area. So I'm just going to use my calculus techniques. I'm going to differentiate. So dA dx, derivative of 3x is just going to be 3 minus 1/2, and the derivative of x squared is just 2x. The 2's are going to cancel there, and I'm going to get 3 minus x. And so, if I set that equal to 0, x looks like it's 3. Now, obviously, x can't be anything negative. It can't be less than 0. So we're not interested in anything less than 0, and x can't be bigger than 6. So we're going to get rid of that. And the derivative here, if it's 0 at 3, if I were to plug in 1, it's positive. If I were to plug in something like 4 or 5, it's going to be negative. So indeed, we maximize the area. And if x is 3 here, y is going to be 6 minus 3 over 2. So in other words, y is going to be 3 halves. So if we have a 3 by 3 halves rectangle, that is the best. That's going to give us the maximum area, not these little tiny things over here or little tiny things right there. That's going to maximize the area. All right, so for Monday, you've got 3 more curve sketching problems because I want you to get some practice with those. They're really important. They will show up on the next exam. They bring together a lot of different things. But you've got 4, I believe it's 4, optimization problems. So, yeah, I think that's 9, 18, 19, and 23. So please take a look at those over the weekend, and you can come on Monday with questions. I may help you set up a couple of those, and we'll go from there. So hopefully you've got a little bit of time today to work on more curve sketching if you want to, some optimization problems if you want to, and we'll convene back here on Monday. Thanks so much, guys.